This is General Physics 1, and we're in Chapter 10. And we're going to start with problem number 3. So problem number 3 says, if you tried to smuggle a solid brick by filling your smuggle gold bricks by filling your backpacks, whose dimension is given, what must the mass be? Okay, so we have 0.54 meters by 0.31 meters by 0.22 meters, which will give us the some meters cubed, and I don't have my calculator, so I will do a pause. So it's going to be 0.037 cubic meters. And then I would imagine that if I go looking for it, I'll find the density of gold on page 261, and it says gold is 19.3 kilograms. 19.3 times 10 to the third kilograms per meter cubed. Okay, and then we would multiply that times the number of meter cubes, and we have 0.037 meters cubed, and our final answer would be in kilograms, which is what we're looking for. In looking at the problem, we only have 2 significant digits, so that's all we would keep in the problem. And it looks like we have 710 kilograms. And probably not something you're going to want to pick up and walk away with. It's a little heavier than you're going to have to have an accompanist list that has a huge amount of body mass. All right, number 4. State the mass and estimate your volume. Hint: because you can swim or just under the surface of the water swimming, you have plenty of good ideas on your density. I do, huh? Because you can swim on or just, okay, so we're going to say my density is going to be the same as water. Alright, well, that being the case, state your, okay, so we're going to estimate our volume. Okay, so you weigh 215 pounds. Close enough? 315 pounds. Close enough?
That's close.
315 pounds.
You got a big guy.
And then we want to change that to kilograms, so we'll take our calculator and we'll put in 315 and second function convert. And English metric guys, we're going to convert gallons to inches, inches to kilograms. There we go, pounds to kilograms. Alright, so we're going to do that on a calculator, and we're going to end up with 143 kilograms. And then we're going to take and divide that by 1,000 kilograms per meter cubed, which is the density of water. and we're going to end up with 1.4 meters cubed, because we're not going to claim to have any more than 2 significant digits. So that's not very much. We can stick you in a pretty small container.
Yeah.
Now, a meter cubed is a pretty big thing. Okay, number 8. And estimate the pressure needed to raise a column of water to the same height as a pine tree. Okay, so we want to go up to 46 meters. Okay, and so the pressure is it not mgh? I'm thinking it is. And yeah, the pressure is going to be mgh. No, it's rho gh. Rho gh. Okay, so the issue is, what is rho for water? And okay, so on page, that's what it is, page 261, and we already knew that. Rho for water is 1 times 10 to the third. So 1 times 10 to the third kilograms per meter cubed times 9.8 times h, which is 46 meters. 46 meters. Now when we get done, we're going to have pascals, because our answer is going to be in pascals. So we'll just put that down. Pascals. All right, well, that's good. 1E3 times 9.8 times 46. And it looks like 4.5 times 10 to the 5th pascals. Now, estimate the pressure needed. All right, well, we don't really have to put that in anything else, do we? But we may want to put that in pounds per square inch. And if we did, we would have pascals per pound per square inch. 1 Pascal is 1.45 times 10 to the minus 4th. Okay, so if we wanted the answer in pounds per square inch, we would take 4.5 times 10 to the 5th pascals, and we'd multiply that times, looking in the front cover of my book, 1.45 times 10 to the minus 4, 1.45 times 10 to the minus 4 pounds per square inch divided by pascals would give me PSI, pounds per square inch, which might be a more useful measurement of the order. Okay, so first answer times 1.45 double E minus 4, and I come up with 65. So at 65 psi, I can push pipe. I can push water up a pipe 43 meters tall, or in this case, a pine tree. Okay. Number 26. A special balloon has a radius, a spherical, not special, spherical balloon has a radius. Up there. Okay, back to what we're doing. 16 is not next, 18 is next, so we'll do 18 next. Not that 16 was difficult, we're just going to do 18 next. Water and then oil that don't mix are poured into a U-tube container both ends are open. They're used to equilibrium shown in the bottom. What is the density of the oil? What is the density of the oil? Okay. So we need a picture. Got a picture. Oh, isn't that nice? And then I've got water like that, and I got oil like this. And I see that I have 27.2 centimeters of the oil, and the difference between the top of the oil and the top of the water is 8.26 centimeters. Okay, so that being the case, then we're going to look at that point there. All right, so that being the case, the height of the water is going to be 27.2 minus 8.62. That's a 2. 8.62. And the height of the oil is going to be 27.2. Okay, and we can throw away this stuff on the bottom because it's just equal to each other, so that stuff on the bottom we don't care about. Okay, so pressure is rho GH. So the pressure caused by the oil, rho of the oil, times 9.8 meters per second squared times the height. Now we're going to have to calculate, though we know the height of the arrow, 0.272 meters has to equal the rho of the water, which is 1,000 kilograms per meter cubed, times 9.8 meters per second squared, times the height of the water, which we haven't calculated it yet. 27.2 minus 8.62. We have 18.58 times 0.1858 meters. Okay, so that goes right here. Alright, so that being the case, rho of the oil is going to equal 1,000 times 9.8 times 0.1858 divided by 9.8 times 0.272. The 9.8s go away, and we end up with kilograms per meter cubed when we get done. Okay, so 1,000 times 0.1858 divided by 0.272, and then we end up with 683 to 3 significant digits, which is all we have in the problem to begin with. Alright, next one is 26. Okay, looking at 26, a spherical balloon. Got a balloon, and the radius of the balloon is 7.15. And looking at the back cover of our book, we see the volume of a sphere is, I think it's the back cover of the book. Yeah, the volume of the sphere is 4/3 pi cubed. 4/3 pi r cubed. Okay, just in case we need that. Alright, back to what we're doing. How large a cargo can it lift? Assuming that the skin and structure of the balloon has a mass of 930 kilograms, neglect the buoyant force of the cargo volume itself. Oh, and we're filled with helium. That's the other thing. Alright, so what we want to do is know the rho of helium. So that would be something that would be cool to know. So we'll go back to page 250, 261, and we see that helium is 0.179. 0.179 kilograms per meter. And well, I'm going to look at that again because I'm not sure what I put down there. Wow. Kilograms per meter cubed. All right. Kilograms per meter cubed. And we also need the rho of air. And from the same page in the book, we find the rho of air is 1.29. 1.29 kilograms per meter cubed. All right, so the difference in those two, the change in rho between air and helium. All right, where's my calculator? There's my calculator. 1.29 minus 0.179. That's 1.111 kilograms per meter cubed. So now all we have to do is know the volume of the sphere four thirds pi r, which is 7.15 meters and the whole thing cubed. Okay, put it in your calculator. It's 4 divided by 3 times pi times 7.15 cubed. Okay, so I got 1.53 times 10 to the third meters cubed. So the mass that can be carried would be 1.111 kilograms per meter cubed minus 1.53 times 1.53 times 10 to the third meters cubed. And we'll make that look just a little prettier. And meters cubed goes away, and the answer is going to be in kilograms. Okay, so I got that number times 1.111, and I end up with 1,700 kilograms to 2 significant digits, if in fact, well, I have 3 significant digits, so we'll put a line there, and that'll make it 3 significant digits. But we forgot the mass of the balloon. Bummer. All right, so we'll have to subtract the mass of the balloon. So we'll have to subtract the mass of the balloon, which is 930 kilograms. And that would be final answer, mass of cargo. Could be 0.7 kilograms. And then we put it on a calculator just to make sure. Yep, that's what I got. Alright, that is a 26 going on to 33. 33. A 32 kilogram child decides to make a raft out of empty 1 liter soda bottles with duct tape, neglecting the mass of the tape or the bottles. What's the minimum number of soda bottles that will have to be used? Okay, so 1 liter. Okay, 1.0 liters is 0.001 meters cubed. If we take 0.001 meters cubed times 100 kilograms per meters cubed, we end up with 1 kilogram. So we have 1 kilogram of water being displaced by each bottle. I think we probably knew that before doing that math, but we know that now. If the child weighs 32 kilograms and we want it to float, then we had better have 33 bottles. Otherwise it's going to be too close to the water line. But I could go along with 32 bottles too, either way. But I like my answer of 33 better, because each of the bottles will have a little soda left in. Whatever. Number 39. Number 39. A scuba tank, when fully submerged, displaces 15.7 meters of seawater. 15.7 liters of seawater. Okay. I wonder what sea it's from. The tank itself is 14 kilograms when full, contains 3 kilograms of air. Okay, so full, 14 kilograms, and empty, I am 11 kilograms. That is what we're trying to tell us there. Assuming only its weight and the buoyance force acting on the tank determine the net force on the fully submerged tank at the beginning of a dive when its air is full, and at the end of the dive when the tank no longer full. What am I calculating? Determine the net force and direction. Okay, so I got to do it twice. So I go here. So I got a full tank. And I'm going to have 0.0157 meters cubed times the density of seawater, which is something greater than 1. And I haven't used it yet, so that means I have to go find it. Seawater 1.025 kilograms per meter cubed. Okay, so when the tank is full, 0.0157 times 1.025 doubly 3, I have 16.09 kilograms of seawater displaced. When the tank is empty, I still have 16.09 kilograms of seawater displaced. Okay? But when the tank is full, it weighs 14 kilograms. So that means it only has 2.09 kilograms left over to provide some buoyancy. When it's empty, I subtract 11 and kilograms, and that gives me 5.09 kilograms. You know, force is going to be in newtons, so I have to go 2.09 kilograms times 9.8 meters per second squared, and I come with some number. The direction is going to be up, so I'm going to be going up, and the force when I'm empty is going to be 5.09 kilograms times 9.8 meters per second squared, and so whatever force that is also going to be up. So in both cases it's going to be going up. 2.09 times 9.8, so I have 20 newtons here. Significant digits, 39. Got 3 significant digits, so we'll call it 20.5 newtons, and 5.09 times 9.8, we'll call it 49.9 newtons. And that would be the force of buoyancy. The buoyant force. Okay, now we're going to go on to 76 trombones. Lead the big parade. 76. Estimate the difference in air pressure between the top and the bottom of the Empire State Building. Okay, so the Empire State Building. That's good. And I'm 380 meters tall. Okay, well, air has a density. We'll go back and find our density on page 261 of air. And I'm not there yet. Now I'm there. Air. 1.29 kilograms per meter cubed. And we want to know, what do we want to know? 76. The difference in air pressure. Okay, so pressure is rho, G, H, and so that difference will be those differences like that. 1.29 kilograms per meter cubed. 9.8 meters per second squared, and 380 meters. And when we get done, our answer will be in pascals, which doesn't help us any because we probably don't like it. 1.29 times 9.8 times 380. 4.8 times 10 to the third pascals. Okay, that's fine. Going back to the front, we really want it in pounds per square inch. So we're going to multiply that by 1.45 10 to the minus 4th. So we're going to find the change in pressure, 4.8 10 to the third pascals, 1.45, 10 to the minus fourth pounds per square inch per pascal. And we'll go back and make sure that's what we got. And yeah, that's what we got. Okay. So I put my final answer as times 1.45 double E minus 4 and it looks like the difference is going to be to 3 significant digits. Is that what I want? Nope, only 2 significant digits. That's better. Alright, so we'll call it 0.70 PSI is the difference between the top and bottom of the Empire State Building. Okay, and with that, we are done with Chapter 10. I'll take Math 1, PHY 168. No, 1 something. PHY 1. I'll get it. Somehow I'll figure it out. PHY 156.
Oh,
Excellent.
I wrote it on the board.
Oh, there it is. I see it.